Thank you very much, Francois, for the kind introduction, and thank you also for inviting me. It's a great opportunity for me to give a talk at the LINX seminars. And today, as Francois mentioned, I will be talking about problems that are related to my project on ERC. It is on distributed function computation on over-communication networks. And here, some of the problems that I will be describing today is joint work with my colleague, Dr. Petros Ilya, and some of his students at Eurecom, and some of my students. And please do not hesitate to interrupt if you have any questions. So this problem of distributed function computation or distributed compression over networks is motivated by achieving a task over a communication network. Instead of transmitting all the data from all the information sources to a receiver or set of receivers, we want to just send as much as data that's needed to be able to achieve a task which we can model by a function. And this indeed has various applications, as you can think, over-the-air computing for IoT devices, where we might want to compute sensor averages, sensor reading averages, or in machine learning tasks in MapReduce or Spark, we generally have to deal with distributed matrix multiplication, which is a very important topic in distributed communication and computation trade-offs, understanding these kind of trade-offs. And other applications such as gradient coding or classification in ML or quantization problems can be also considered as a subcategory of this broad class of applications. But here in this talk, I only focus on the compression or computation problem over a physical network, which has some constraints. And why do we want to compress data? First of all, when we want to compute a task or perform a computation, in general, in networks, we have limited resources. This could be in terms of the transmit power of the users, or it could be because of the link budgets, bandwidth, etc. We do not want to waste resources by sending the set of all information sources. Or we might have privacy constraints. For example, we want to achieve a task, but we only want to send as much as to perform the task without revealing the identity of users or more sensitive information. Or in general, when we consider distributed settings, there could be some overlap across the data sets belonging to different set of users, and we do not want to cause redundant transmissions. We do not want, we want to exploit the correlation between and across the sources to be able to compress them well, to be able to perform the desired computation. So these are the main motivations for distributed computation. And there is a lot of related work in this direction. So from an information theoretic perspective, this problem has originated around 1970s. So with the work of Sleppy and Wolf on distributed source compression, and also their extensions to more practical coding schemes by Ramchandran and Sandeep Pradhan, as well as the generalizations of the rate region models by using graph entropy techniques by Kerner, Orlitsky-Roche, and many other names that I am not able to list in today's talk. The problem has been studied for describing and understanding the rate region using a graph entropy perspective. And also some special cases of this problem corresponding to computing linear functions has been extensively studied. But when we consider more general functions that are not linear, we do not have a unified framework. So, and it's because it is hard to understand the relationship between the functions we want to compute and the restrictions imposed by the topology of the network. So this is the focus of today's talk, in which I do not give a unified solution, but I give some perspective that can be exploited to understand the bigger picture. So what do I mean by a distributed function computation setting? This setting includes multiple servers or workers. In this setting, there are n workers. And let's denote the data contained in a worker I by x of I. And this x of I could be correlated. And we have a master node that's interested in recovering a set of functions, fj. Let's say there are kc functions that the master is interested in recovering, and these functions are multivariate functions of all these workers. And the workers transmit some information to the master, and they are distributed, which means they cannot communicate with each other. And the master is only interested in recovering the set of these functions. Okay, our goal is to understand what is the minimum sum rate that we need from the workers to be able to recover the desired function at the master in a lossless sense, which means that we need to consider the asymptotic scenario as the block length goes infinity. And needless to say, if you have questions at any time, please do not hesitate to ask them. So in the general setting, we assume that we have k data sets, capital K data sets, indexed by this variable small k. And we have k messages that are these univariate transformations that are being stored at each server, wk's. And we have n distributed workers. The set is denoted by this omega. And each of these distributed workers contain a message set, which is denoted by xi, which is nothing but a subset of the set of entire messages. And that subset is denoted by zi for the worker I. So this subset is a subset of these k data sets. And the master requests kc messages, kc functions of these distributed sources given by this set of functions. And we have this parameter nr that is modeling the number of workers, the minimum number of workers that we need to wait for to be able to recover the set of functions. Okay, sometimes a subset of servers is sufficient to recover the desired functions. And this becomes important in the settings where we need to deal with stragglers. And here we also have a minimum computation capacity per worker. It is given by this expression, which is given by the notation n. This is indeed describing the set of messages that are included in a given worker. So these are the set of parameters that I will have in most of my slides. So there are some additional assumptions in this talk on in terms of the placement of the data. For example, this is also a general assumption in the recent work that has been done in this direction. We assume that the data set assignment across the workers has been performed in a cyclic manner. So more generally, like this set of indices that are placed in a given worker follows this rule. If I consider a simple example to describe it, if I have 3 data sets, 3 workers, and NR is the recovery threshold, which means that 2 out of 3 workers, any 2 out of 3 workers is sufficient for me to recover the desired function. And n equal to 2 means that each worker contains 2 data sets. Okay, for the cyclic placement model, so I have 3 data sets, D1, D2, and 3. I place the D1 and D2 here in the first server, D2 and D3 in the second one, the D3 and D1 in the last one. You see the cyclic pattern in placement. We are not restricted to have this model, but this is this model allows us further simplification. And it looks nicer if we have this assumption, but we are not restricted to have this assumption in general. So let's consider an example which is motivated by practical applications. Let's say we have n distributed workers and we want to compute a matrix product in a distributed way. So we have an A matrix and B matrix. And we are expanding the A matrix in terms of the columns that it has. It has n columns. Okay? Each column is a length 1 column, and it's just a column vector. And similarly, we expand the B's into multiple rows. Each row is going to be a row vector, and there are n of them. So more formally, we can consider this one of these columns to be a length n column of A. And this one, the kth row of B is also a length n row of B for this specific example. And under the cyclic placement assumption, when we have n workers, the dataset assignment, given that I'm allowed to put two sets of items per worker, X1 contains W1, W2, X2 contains W2, W3 in a cyclic manner, and Xn needs to contain Wn and W1. And here, for this specific problem, I assume that Wk, the message functions, are nothing but the subset of columns of A matrix. For example, Wk is nothing but the kth column of A and the kth row of B. So this is intentionally being done like this because it promotes the diversity across multiple workers. So again, if we consider an example, it means that for this specific example, X1 contains two columns of A, A1 and A2, and two rows of B, B1 and B2. Similarly, X2 contains the second and third column of A, and the second and third row of B, and so on. And the master node wants to compute the product of A and B. In this case, we only have one function that is requested by the master. Kc is 1. nr here is n minus 1. So these matrices have n columns. A has n columns and B has n rows. So I need to get these distinct columns and rows to be able to perform this computation. And to be able to recover n distinct columns, I need to be able to access to any subset of n minus 1 workers that will provide me the required number of columns and rows in my matrix. And here, K is modeling the number of data sets. So the matrices are each n by n in this example. So each matrix contains n square elements, and I have two such matrices. And the computation capacity of each node is determined as 4 times n for this specific example. So again, we can consider more general functions. We are not restricted to computing the matrix products. We can consider the identity function, which boils down to recovering the sources themselves by the destination. This problem has been studied previously, both for the distributed setting or also for the settings with side information. Or we can consider affine functions, linear combinations of the source symbols. We can also consider bilinear functions, or we can consider more general nonlinear functions like matrix multiplication, or we can go to one step ahead, consider sparse polynomials or more dense polynomials. And I can increase the number of examples, but for this talk, I will only consider very simple examples that we can understand easier. And of course, we can do the computations of such nonlinear functions or linear functions in single shot or multi-shot settings as the block length goes to infinity. And the goal is to understand how much rate we need to be able to perform this computation by the master node. So that will describe the minimum total communication cost of all the workers. So I need to give some background on distributed source coding to make you more familiar with the concepts. So computing the identity function is indeed the problem that was studied by Slepian and Wolf in their landmark paper. So here we have two distributed sources, X1 and X2, and the destination wants to recover them jointly and in a lossless manner and in an asymptotic manner. And the variation of this problem is also known as the side information problem, where the destination again wants to recover the sources, two variables jointly, but one of them is available as a side information. But our setting is more similar to the first one. That's the one that I want to describe quickly. So here, Slepian and Wolf have demonstrated characterized the rate region for this problem proving that using some very simple random binning arguments, the rate of source 1 can be given by the conditional entropy of that source, given the second variable, similarly for the second source. And the surprising result is that even though the sources are distributed and they cannot communicate with each other, the sum rate can be made as small as their joint entropy. And you know, for two random variables that are distributed according to P, X, Y, the best rate at which we can compress them, if they were located in the same place, that would be their joint entropy. But even in the distributed setting, it is possible to compress up to this fundamental limit. That is the strength of their result. And the achievable rate region is indeed the curve that is lower bounded by this, the region that's lower bounded by this curve. Okay, so this is the summary of computing the identity function. But as you can see, the approach that Slebien and Wolf has provided, it is for recovering the sources themselves, and it does not think about the structure of the function. So, and the random binning arguments that they provided cannot be directly applicable to computing functions. So this is indeed a rate region that is, this is a higher rate than what is required to be able to compute functions instead of recovering the data. So just to give a small example, when we want to compute a function that's different from identity function, this is an oversimplified example, but explains the core idea. Let's say we have x1 and x2, and at the receiver, we want to compute the modulo 2 sum of x1 and x2, and the alphabet of x1 is 0, 1, 2, 3, alphabet of x2 is 0, 1, and at the end, we want to compute a binary result, right? So here, I know that even though x1 and x2 cannot communicate with each other, they can form some equivalence classes between themselves. Because given that they know the function, I don't mean the output, but given if they are instructed the function at the destination, they can classify the source in a way that which source subsets yield the same output and which source subsets should be distinguished from each other. For this simple example, we know that 0 and 2 at source 1 will yield the same outcome, because when we consider modulo 2, 2 will be the same as 0. Similarly, set 1 and 3 will be in the same equivalence class. So what they do is they color these different equivalence classes by using by using colors. For example, 0, 2 is mapped to color blue, 1, 3 is mapped to color red. And instead of sending the original variables, they send these mapped variables, the coloring variables, and that provides saving in compression. For this specific example, we can provide 1 bit of saving by doing a compression for the function. The second source cannot do much compression because it already has 2 binary outputs. They need to be distinguished. So here I try to illustrate this idea in this figure. So this upper curve denotes the lower bound for the Slebien-Wolf rate region. And in doing computation, it is possible for us to shift this lower bound closer to the origin. And the gap here, it depends on the function, and it depends on the scheme that we develop to achieve the feasible, to achieve the desired compression rates. So let's see how we can model the compression by using a graph entropy approach. So here the idea is, this is based on Kerner, and again, the work has been done in 1973. The idea is to use characteristic graphs. What is a characteristic graph? A characteristic graph has a set of vertices. The vertices are the possible values that a random variable can take. Okay, we want to compress x1. It can take 5 different values uniformly at random. So this graph will have 5 vertices. Okay, and then we need to determine how we decide the edges between these vertices of the graph. So the way that the edges are decided is based on whether we need to distinguish the 2 possible outcomes of the source or not. For example, in this example, the first outcome, 0, the second outcome, 1, we need to distinguish them because it can cause a confusion at the receiver. They need to be distinguished. But for example, C1 and C3, when any of these outcomes are sent, we know that it does not, 0 or 2 is sent, it does not cause a confusion at the receiver. There is no edge between them. So we don't need to distinguish them. And similarly for the other vertex pairs, we need to figure out whether we need to distinguish them or not, and we determine how to place the edges accordingly. Once we build the graph, then the problem becomes how to do the coloring of this graph efficiently. For example, if for a pentagon like this, we need 3 colors. We cannot do a coloring more efficient than this. And when the samples are uniform, the coloring distribution of this graph is like I have to use this red color twice and the purple twice. These will have a distribution 2 by 5, 2 by 5. And this yellow color will have a probability 1 by 5. And when I evaluate the entropy of this coloring, I obtain it's 1 by 1.52, which is less than the entropy of the original source, log 2 of 5, right? So this is a simple way to understand the savings that we can obtain using a graph entropy approach. So this gives us the true rate region. This helps us give the true rate region for functional compression at a very high level. So more formally, we can determine a chromatic entropy of a graph. Let's say for the previous example, we found a coloring for the characteristic graph G of X1. And let's denote that valid coloring by the C sub that graph. And the entropy of this coloring for the minimum entropy coloring gives the chromatic entropy of this graph, which is denoted by this expression on the left-hand side. And what Kerner has shown was, this is a very strong result, the graph entropy, the fundamental rate at which we can compress a graph, is nothing but given by this limit. So we need to take the end power of the graph that we build that corresponds to the realization of the source variable and length and realization of the source variable and building the graph for that realization and compressing that graph. So if we find the coloring for the length and realization of the source random variable and take the limit as n goes to infinity, that will give us the fundamental limit of compression. So in a distributed setting, what happens is, instead of compressing the sources themselves, each source builds a graph and it sends the colors of that graph. So we need less colors than the information bits we have. And the destination, by using the received colors, it can help decode the function. And this provides us reduced transmission rates from the sources. Just to explain what I mean by the power graph, if we have a graph that is built for the original random variable, the thing is, in an information theoretic setting, we cannot consider one-shot transmission to understand the fundamental limits. Like, we need to repeat the experiment infinitely many times so that we understand the fundamental limits. The way we build this graph in a lossless compression scenario, it is a OR graph. So in the first realization, we have 5 possible outcomes. In the second realization, in the 2 realizations, we will have 25 possible outcomes. You will see on the right-hand side, we have the second power graph with 25 possible outcomes. And the idea here is each subgraph is identical to the first graph, but we have the consecutive subgraphs here that you see. They are fully connected. The neighbors are fully connected. This is how we build a OR graph. So here, the idea is when we do the experiment sufficiently many times, we can reduce the number of colors we need on average. For example, for the first power graph, we needed 3 colors. So this 3 by 1 coloring means that when I'm adding 1 color per vertex, only 1 color per vertex, and I need 3 colors in total. Whereas when you look at the right-hand side, Intuitively, we know that 9 colors would be an upper bound, because for the first realization, I need 3 colors. If I consider the second realization completely independent, I need 3 colors, and the combination has 9 colors. But we can show that with this OR graph, we require only 8 colors, which is less than 9, even though it is not significantly less than 9. So, and my work has been based on these existing results. And I have recently generalized by exploiting the structures of the functions. How can I use the coloring arguments to provide better compression for computing? Indeed, the idea is very simple. So what I want to do is, instead of considering assigning 1 color per vertex, I want to assign multiple colors per vertices. So let's consider the same example where I can do a 3x1 coloring. Let's repeat the same example and use a different set of colors. Or instead of blue, I use yellow. Instead of orange, I use purple. Instead of green, I use red. And then let's take the average of these two, okay? So for this node that is modeling the index with text value -2, I have blue and yellow. And for this node, let's say I have orange and purple. Each node is assigned with 2 colors. In this setting, as you can see, since I'm just replicating the same graph and assigning 3 colors per realization, in total I have 6 colors. And now I have a 6x2 coloring. Of course, this is not the most efficient way for coloring this graph, because every time I use 3 disjoint colors, there is no overlap across these graphs. So my idea was to see there could be some overlaps in terms of the colors that we are using. For example, okay, I think I copied the wrong figure here. Okay, what I did was, in the second figure, instead of using this same coloring with 3 different colors, I can provide a 5x2 coloring. So you can, if you look at the right-hand side of the last graph, this node is assigned yellow. This node is assigned yellow. These 2 nodes with 0 and 2 is assigned purple. And you see this node is assigned green. And I know that in my original graph, I had also assigned a green to this vertex. But what I can notice is 0, node 0 is not a neighbor of -1. Therefore, when I replicate the same experiment, I can reuse the same color. And instead of 6 colors, for the second graph, by using 2 extra colors, I am able to achieve a 5x2 coloring, which provides me a saving. And this saving is just by exploiting the structure of the graph that comes from the structure of the function. And indeed, without going into too much the technical details, we can compute the entropy of this graph by finding the distribution of this coloring. And it is possible to show that even for this one-shot realization, we can gain 0.36 bits, which provides almost 25% saving. So the key idea here is, how can we compress further by using fewer and fewer colors? And it is possible with fractional coloring, because in fractional coloring, the idea is I can assign more colors per vertex, but I am not allowed to have overlapping colors across vertices that share an edge. This is a generalization of the traditional coloring. So, and of course, the idea becomes more interesting when we consider higher power graphs. So in the example with standard coloring, we know that we need 8 colors, and we can do an 8x1 coloring if we consider the traditional coloring, which is shown in the left figure. But when we consider 2 colors per vertex, I don't claim this is optimal, but when we consider 2 colors per vertex, it is possible to use 13 colors in total. On average, 13x2 is 6.5, which is less than 8, and this indicates a saving in coloring. So some theoretical notions, for example, the psi of B denotes the B-fold chromatic number. For example, for the graph on the left-hand side, it is 8. Sorry, it is 3, because I'm doing a one-fold coloring per vertex. And for the second power graph, it is 8. But for the second graph, the B-fold chromatic number, it's going to be 30. And indeed, there is a very nice result that relates the B-fold chromatic number to the fractional chromatic number given by this expression. So in the limit as B goes to infinity, the ratio of the B-fold chromatic number to B gives us the fractional chromatic number. For example, if we consider this small graph, the first order power graph, I have 5 colors. I have 5 vertices, but I need 3 colors in total. It can be shown that the fractional chromatic number for this graph is indeed 2.5. And if I go back to this example, indeed, this 5x2 coloring for this example is optimal. There is no other way to find a better coloring for this example. It's the most efficient coloring. And there is a very nice theory and behind these fractional graph theory arguments. I have been recently reading a lot. And this theory has been, if I see the reference, I will point out. There is an easy way to determine the fractional chromatic number as a solution of a linear program. So this linear program is over the independent sets of the graph. It can be determined by solving this linear program. Even though I say linear, as you all know, as most of you know, that determining the independent sets of this graph, an arbitrary graph, might not be easy. Sometimes it is not NP hard. So solving this problem heavily depends on whether we can determine these independent sets. But after that, it is easy to show that this fractional chromatic number indeed provides a lower bound to the actual chromatic number by assigning 1 color per vertex.
Derya, can I ask a question?
Of course.
Could you explain in a few words in the earlier slide why the limit exists and why it corresponds to the inf? Is it difficult? Just the existence of the limit when this B goes.
Okay, it's a very good question. Let me try to explain. So this psi B function, it increases as function of B. It's an always increasing function of B. And as far as I know that its limit exists, and okay, so the ratio.
Superadditive or subadditive function?
It is a subadditive function. It's because of that. Yes, thanks a lot. The main reason is the subadditivity. And this linear programming is indeed very simple to solve once you know how to determine the independent sets. For the examples that I have shown, it is not difficult, but for more general graph theory problems, it could be very difficult. So, but even though we cannot determine this number, we always know that this number provides a lower bound to the chromatic number of a traditional coloring. So what I have done, I don't know how am I doing in terms of time, but it's okay, I guess. So what I have done was I evaluated the entropy. I characterized the entropy for this fractional setting. And I characterize the fractional chromatic entropy. So here in the above, I have a definition where instead of standard coloring, I define a set of valid colorings, fractional AB colorings for a given graph. And then over the set of fractional chromatic entropies that I have defined for this set, I find the best coloring that minimizes the entropy. And the solution of this problem will give me the fundamental limit of completion for the more general setting where I can allow more colors per vertex. And here, by using this chromatic entropy, we can use it to determine the fractional graph entropy, which is nothing but in the limit as n goes to infinity, and in the limit as b goes to infinity, by computing the entropy of this large power graph in a fractional sense and taking the limit. I know that these expressions do not look as very appealing, but these limits indeed generalize the traditional limits that have been derived by Orlitsky and Roche in their 2001 paper, using a very simple approach. And one of the main results that I had was like to show that this fractional graph entropy is indeed a lower bound to the original graph entropy. And these results can be shown by using the very useful reference that I am citing here by Schneierman. The title of the book is Fractional Graph Theory. Indeed, there are very beautiful relationships between the fractional chromatic number and so g to the n denotes the nth or power of this characteristic graph that we build. It is related through this relation. This relation allows us to approximately describe the nth power of the fractional chromatic number and the chromatic number for the nth power of the graph. So this is a very nice relationship. And by using this also for the fractional chromatic number, we have another nice relation for the odd power graph, the fractional chromatic number for the odd power graph. All power graph is the same as the fractional number raised to the power n. This indeed provides lots of simplification because determining this all power graph is not very easy. But determining the fractional coloring number for simple n equal to 1 power is rather easier. And I have also characterized the integrality gap, which is indeed the savings of using this fractional coloring approach over the traditional coloring approach. And here there is a parameter that I didn't explain, but this parameter shows the optimal value of B. Remember, B was the fold of coloring, how many colors that I assign per vertex. And this integrality gap between the traditional solution and fractional solution can be characterized by this expression under several additional assumptions. Is there a question?
So I'm not sure to understand what you mean by optimal B. I mean, you said it was, I mean, in the earlier subadditive thing, it was the inf, right?
Yes, it is the inf, but it is possible that we achieve the same result before we reach there. For example, for this graph, I can also do a 10 by 4 coloring.
I see.
Which will be identical.
I see. Okay.
But in general, yes, it is a subadditive function, and we might need to take that limit.
Okay. And I suppose these are very difficult things to compute. I mean,
these are very difficult things to compute.
Yeah, because
yes.
you have to do that for right. So you have to explore lots of B's, right? Sort of. And
that is true.
And each problem is difficult, right? So that is
it is indeed very difficult. But what I have done was just to demonstrate that I can do something better than the existing theory. And I did only some examples for simple scenarios and some binary encoding for such scenarios without complicating, without needing to compute higher order power graphs. And but in general, it is difficult, yes.
Yeah. Are there cases where one knows the limit? I mean, you alluded to cases where you had the optimum, but are there broad classes where you know how analytical expression for the limit?
So this, if we can solve this linear program, then we have it. But unfortunately, like if the graph, if we cannot characterize the independent sets of this graph, it might not be possible. But I know that there are approximations to determine the independent sets. So then we might end up with approximations for this fractional chromatic number. Thanks. But there are very nice results that upper and lower bounds these fractional coloring numbers. Again, I don't know what those approximations tell in an information theoretic sense, because they prefer exact relationships. But these approximations could be very tight as we increase the length of the sequence. And that could be some useful, it could be very interesting to explore the endpoints of the lower and upper bounds to understand the fundamental limits of compression, perhaps. Okay. So I know that I have deviated from the initial problem that I described, where we had this distributed matrix multiplication, because I had to go back and describe the distributed source compression problem, and to move to the graph coloring approach and the refinement that I have devised to improve the graph coloring approach. Now I go back to the initial problem that I described, which is more practically oriented. So using the graph theory approach, it is possible for us to model, to characterize a rate region for a subset of servers. So this omega was the set of n servers, and S denotes a subset. And this is a trivial extension of the Slepian-Wolf bound for any subset of users. The sum rate needs to be lower bounded by the conditional entropy of the given subset, given the remaining set of sources. So this needs to be satisfied for all the subsets of the servers, where the definitions for this graph entropies and the conditional graph entropies are written here. So I know that it looks a bit complicated, but what it all says is the graph entropy is nothing but the best entropy of the best coloring that we can find for coloring the length n sequence, and similarly for the conditional graph entropy. So we need to be able to understand the fundamental limits for communication, distributed communication. We need to evaluate these terms. And we can also say, yes.
Sorry, can I ask a question? So could you explain again the connection between the function and the graph? I'm sorry, I did not follow.
Okay, maybe I can go back.
Right.
I'm sorry if it was not clear.
No, just we are slow. I am slow.
So here, the source x1, there is another source x2. They cannot communicate with each other, but they know a multivariate function f of x1 comma x2. So the source x1 needs to build a graph without knowing what x2 was. It only builds the graph according to this function, bivariate function, and the outcomes of x1. So let's say this is the first outcome. Like in this example, my outcomes are 0, 1, 2, 3, and 4. And the source needs to decide out of, like, in total, I might have 10 edges in this graph, but I need to decide where to place, like, I need to decide if I need all these edges, because if I used all the edges in this graph, basically I don't provide any compression, then it becomes a complete graph. I need to use distinct colors for all the possible outcomes. With function, I'm seeing that it is possible that I need less edges and that can provide me savings. And the way I decide to put edges here, I say that, okay, when x is 0, x1 is 0, or x1 is 1, there exists at least one value of x2 such that the function f of 0 comma x2 is different from f of 1 comma x2. If there exists such only one x2, then I need to put an edge here. If there is no such x2, then I don't need to distinguish these two vertices from each other.
I see. Okay, thank you. Yes.
Okay. It is a bit more complicated than this, but it boils down to this idea. Like the joint distribution needs to also be valid in that specific coordinates. It needs to be non-zero in those specific coordinates. Okay, so once we know how to construct the graph, the rate region is not hard to determine. It can be determined using this entropies for this multivariables that models the set of sources that we want to compress. And like more formally, if we want to compute the communication cost of a specific worker, we need to, okay, for a given block length n, we first need to build a graph, and we then need to find a coloring, which is denoted by this variable, okay, for computing this multivariate function. And then instead of encoding the variable xi, we will do the encoding of the colorings, these C variables. And I denote the encoding by E of xi of this coloring. So this will be the transmission of my worker. And what I need to compute is the entropy of this transmission, entropy of this transmitted variable. And the ratio, the length, the entropy of this vector of coloring divided by the length of the transmission, it will give me the rate for transmission. And indeed, it is lower bounded by the graph entropy. There are some extra symbols that I don't think it is essential right now, but the key idea here is that the compression rate cannot go below the entropy of the graph. So for the example scenario, if we go back to that, what I did was I considered n servers and I considered various examples and I evaluated the rate region for these examples. The first one is the summation. So I have these messages that are k messages that are distributed across n servers. And I want to assume that n divides k, so k is a multiple of n. And it doesn't need to be like that, but it simplifies the expressions. And I want to compute the modulo 2 sum of these messages. And the rate region for this problem, depending on the subset of servers that we select, it is characterized by the expression on the right-hand side. For example, we know that we need at least NR servers for this problem. So if we select a subset that has cardinal, is there any question? Okay. Okay, so if we select a subset with cardinality less than n by n minus nr, it is not possible. The sum rate of those subset of users need to be 0, because when I look at the expression for graph entropy, on the right-hand side, I will have the remaining nr users, and any subset of nr users is sufficient for me to recover the function. That is why this subset of rates will be, the sum rate for the small subset will be 0. But if I enlarge my subset, if I am in this regime, I need more and more rates from the individual users. And here, in total, I have n workers. If we look at the last expression, I know that each of these n workers contains n minus nr plus 1 times k by n. This is the computation capacity of the worker. Therefore, the rate it needs to transmit will be inversely proportional to that. This is a way to interpret this result. And between this first line and third line, I have this intermediate result where the rate is smaller than here. And it is determined by the set of workers that I am conditioning on, the set of messages that are cached in those subset of users. And I can generalize this idea, I can apply it to the other functions. For example, rederiving the Slepian-Wolf region for this specific problem. Let's say I want to compute a function. It's an identity function. And in this case, the rate region is simpler. So I have in total k data sets. I have in total k functions. And the sum rate needs to be k. So I cannot avoid it, as provided that all these messages are identically distributed and independent of each other, their joint entropy will be exactly k. And in between, we have some reduction depending on the subset of users that we are conditioning on. And so when we have more sophisticated models, when the data sets, the messages are not uniform, they have some skew distributions like parameter by epsilon, we can get more complicated expressions, but it just looks complicated, but it is not very non-trivial to observe them. I think what we need to do is we need to find the minimal set in art that contains the desired, that contains the sufficient information to be able to recover the desired function. And here, the minimum number of workers that must transmit is given by n star. And each worker has n minus nr plus 1 data. And n is the number of workers. Their ratio is approximately giving us the number of workers that needs to transmit. And maybe if this is if n is not a direct multiple of n minus nr plus 1, I need an additional worker that needs to do some partial computation. And that partial computation is modeled by this part. And this remaining part is the one that needs to be sent from the n star users. And each user, since it contains a subset of items, it can do that local computation and determine the parameter of the modulo 2 transmission. And that parameter can be recursively computed using the parameter of a Bernoulli distribution. Since I am running out of time, I think I will just skip this. And we have also extended this result for bilinear functions. And if I quickly move to the simulations, I apologize for the delay I caused. We can show that compared to the approach where we do everything in a distributed manner without taking into account the function structure. So this solid curve shows the gain of the graph entropy approach over the distributed approach of Slepian-Wolf. And it is possible for computing the summation function. It's possible to obtain gains larger than 30% as a function of the skew parameter of the distribution. And these gains increase when the capacity of the computation at the server increases. And the other curve denotes the comparison between the best possible rate as if every data was stored in a centralized location, which is not possible for us to achieve. So the graph entropy approach is clearly worse than that. And also for the bilinear functions, because we are computing products, as the skew of the variable increases, the gains become higher and epsilon is very small. And it's possible to achieve significant gains larger than 90% for this specific example, for example. And I just want to leave in this conclusion slide, and I'm happy to take any questions you might have. Thank you very much.
Thank you. Any question in the room? Yeah. Yeah, two questions. It's fascinating that for various classes of function, you can really give this. Did people investigate like tropical functions? I mean, involving max and mean or tropical polynomial, things of this type?
So I am not very familiar about tropical
polynomials. Just to say max or mean or...
Okay, I see maybe from like a sigmoid perspective of machine learning applications.
Of course, people might have been interested in some fields that are currently under investigation in ReLU and things like that.
I am familiar with like some classification approaches where instead of modeling them using the min function, maybe it is like a hyperplane based approach. Instead of having one threshold, there are multiple adjustable thresholds. So you're modeling the function as a function of these multiple thresholds. It will be like a vector quantization of the source sets.
I see. Right. And so, but in principle, I mean, so of course, I understand that you have to solve this linear program, right? But in principle, I mean, you can apply this methodology to any function, right? Provided, I mean, these are finite sets of values and finite sets.
Yes, right? Yes. As long as the source has finite alphabet, and if the function is, again, as long as the source has finite alphabet, and if the function is sparse, sufficiently sparse, because like we do not want to deal with complete graphs. If we have more savings, if we have sparse graphs, as long as we can achieve a standard coloring, it's always possible that we can take that standard coloring and refine it using fractional coloring. And it can provide significant gains when we have sufficiently long block lengths.
And if you just ask for the max, I mean, is it no? Or is it trivial? Perhaps it is trivial?
It is not trivial. Even when we ask for, let's say I have X and Y distributed, even when I want to compute X plus Y, it is not trivial.
Okay.
There is indeed, it is also an amazing result by Körner and Marton. I think that result is also from 1980s, if I am not wrong. So they have generalized the random binning approach of Sleppy and Wolf to a structured binning, where they are exploiting the homomorphic relationship between the bins to make sure that they nicely align the bins and at the end reduce the rate they need for computing that addition function. Indeed, what would be nice is to be able to, if we can consider more general functions, and if we can simplify them or approximate them in terms of additions, or a combination of some addition functions, it is possible to use their approach and get some insights. But as far as I know, if beyond addition function, there is no fundamental result. Like most of the theory has been performed for the linear function computation.
Thank you. And so my second question was, I mean, you have discrete alphabet and discrete. So, I mean, is there any meaning of a theory in the continuum?
That's a great question. So information theorists, they always use discrete alphabets, generally binary alphabets. And indeed, for the binary alphabets, this graph theoretic approach becomes very convenient. When we consider the continuum approach, I believe if we are allowed to tolerate distortion, because it is impossible to recover continuous variables over discrete channels, I guess, if we are allowed to use a rate distortion-based approach, it is possible that we can quantize the sources according to the function we want to compute. So it could be a vector quantization approach, where the way that we decide how to put the edges can depend on how much error we can tolerate by switching one coordinate to another. But I am not familiar if there has been any work on that direction.